Okay.
Playing from laptop, I want go to
Okay, thank you so much. Let us start the session. Okay, so today actually we'll discuss the week 9 assignment. Okay, the week 9 assignment is mostly the last lecture we have means in the last lectures we have covered actually the compensator design. Okay, how to design the compensator using root locus approach. But here in this we have to design the system using Bode plot analysis. Okay, how you want to maintain your system stability. Okay, by using Bode plot. Okay, so I'll show you some of the questions that related to Bode plot and also how to deal with in MATLAB. Okay, how to find out the system stability parameters. Okay, so let us discuss one by one what are the things that the last lectures means last video series that covers mostly. Okay, so let me write fast something. Okay, so can please just confirm that actually my screen is visible because just started my recordings. Okay, please just confirm it that my voice is clear and the screen is visible. Okay, I actually am not getting any response. Can please someone? It's okay. Okay, let us start. Okay, so so here actually we're going for the uh, design of the system. Okay, so basically the design of the system using Bode plot. Okay, so system design means suppose you have a system like a plant, you can say you have a GS which transfer function is given. So now here what I do to add, I need to add a compensator. Okay, I have to design this compensator so as that to meet the time response specification or to meet the stability of the system. Let's say this compensator gain is GCS. Okay, here this is your output, this is your input of the system. Okay, now this compensator, it can be a lag compensator. I already discussed previously lag compensator. It can be a lead compensator. Okay, so sometimes you need to design the lag compensator system gain or the lead compensator system gain. Okay, so we'll see a lot of question based on that. Other things what you need to do, you have to do the stability analysis. The stability analysis in Bode plot is just a frequency response plot. Okay, this is just a frequency response plot. So you need to find out the system stability. So what are the parameters that will decide that? So you need to find out the gain crossover frequency, or you can just simply call gain margin. The gain margin you can find out. I'm just writing it. Gain margin. You need to find out the phase margin. Simply the gain margin you need to find out at phase crossover frequency. Omega PC you can say. Okay. Yes. The gain crossover frequency corresponding to omega PC and the phase crossover frequency corresponding to omega GC. You need to find out the bandwidth of the system. Okay, bandwidth means this is the bandwidth. You need to find out the resonant peak MR that already are discussed in the lecture series. Okay, resonant peak. Okay, so these are the things that you need to find out. Okay, using the Bode plot analysis. Okay, so I'll just start with a brief introduction. I'll just give about the lead compensator and lag compensator. Then we'll go to how to find out the gain margin, phase margin, bandwidth, and all these system stability related parameters. Okay, so let us move to the next slide. So before that, actually, the first question what tells us you to find out the gain margin and phase margin of the system. This is a basic question I put because I just want to give that how we are finding out the system gain margin, phase margin, and everything, all these parameters from the Bode analysis. Okay, so there are two approaches. Okay, you can do by calculations. Okay, other way is that you can use MATLAB. That's MATLAB is a very powerful tool so that this kind of responses you can easily find out. Okay, so I'll show you one or two MATLAB demo so that how to find out the gain margin and phase margin, how to plot the Bode plot of the system. So uh, let me quickly for the first question, can anyone uh, try this question? How to find out the gain margin and phase margin for the first question? So what the question is given to you? You have given g of s is given to you. Okay. So first of all, what you convert? You have to convert into frequency domain. J of omega. What is this j omega omega? E to the power minus 2. Okay. And this, in place of this, you have to write j omega. Alright. Divided by j omega into j omega plus 2. Okay. So he's asking about to find out the gain margin. The gain margin is always you have to find out as phase crossover frequency omega pc. This is called the phase crossover frequency. So what is phase crossover frequency? Phase crossover frequency is the frequency, okay, at which the phase angle is 180 degree. Okay. And what is similarly phase margin? Phase margin is the always you have to find out at omega gc, the gain crossover frequency. Gain crossover frequency is the frequency at which your gain of the system equal to 1. Okay, it means you can say that g of j omega, this magnitude is equal to 1. Okay, so let me find out. Okay, uh, so what we need to do, first of all, you need to find out the omega gc to calculate the phase margin. So now I am interested to find out this omega gc. So how to do that? Omega gc, you have to take the magnitude of the transfer function and make it equal to 1. Okay, so this is a very important question. Why I put that? Because here in this question we are putting a transportation delay. E to the power minus 2s, this term is a transportation delay term. Okay, transportation delay, or simply you can call it delay of the system. Okay, it makes the system delay. Okay, or it can sometimes make the system advance. Okay, so let me find out what is omega gc of the system. Please everyone mute yourself. Okay, 3 into e to the power minus 2 j omega divided by j omega into j omega plus 2. I'm just requesting everyone to kindly please mute yourself. Yes, thank you. Okay, so you just make it equal to 1. Okay, so what is the magnitude of the denominator? Can anybody tell me? E to the power minus 2 j omega. What is the magnitude of this one? This is nothing but you can write out it is cos 2 omega minus j sine 2 omega. Okay, so if you find out the magnitude of this, okay, this is just the sine theta or minus j cos theta, like that. you take the magnitude of this will equal to 1. It means the magnitude of this term means especially this is the magnitude of this term which is now equal to 3. Okay, so because e to the minus 2j omega magnitude is 1, magnitude of 3 is okay 3. So now I can write down 3 divided by
Your voice is breaking, not clear.
what is not clear?
Voice, not clear.
Voice is not clear.
No, sir.
Now it is clear.
My little noises when you speak.
Uh, I think from my side there is no problem. Okay, you can check yourself because I can able to see and listen my voice is okay. It is clear from my side. If there is still some problem, then it is
Now
clear.
okay, now okay.
Okay, thank you so much. Okay, so what you do, you just find out the magnitude of this. Okay, so omega square you can 4 and make it equal to 1. Okay, if you take a square of this will be 9 into omega square plus 4. Okay, you just simplify this equation. Okay, so what is will be, this will be omega fourth plus 4 omega square. If I take this minus 9 to 9 to the left hand side, right hand side, it equal to 0. Okay, now this is a fourth order equation. Okay, you just try to solve this equation. How to solve this equation? You just put omega square equal to x. Okay, then what is the equation will becomes x square plus 4x minus 9 equal to 0. If I put this here, okay, then this will be here like that. So now you can find out what is the value of x. That's this is a okay quadratic equation. You will find two values of x. Okay, one is x1 and x2. Once you find x1 and x2, then you find it omega. Omega is nothing but root over of x1 and root over of x2. Okay, so you can easily find out this value using using calculator, because in your examination MATLAB is not allowed. So better what you do, you practice using calculators. How much calculator you can use freely, that will help you in your examinations. Okay, but this type of thing, if MATLAB is be allowed, let's say you are designing a system. Okay, you are working in a company, or you want to, you are a teacher, you want to tell the things to your students, then these are the things you can easily plot in the MATLAB to find out what is exactly in one command. It will give you the gain margin, phase margin, gain crossover frequency, and phase crossover frequency. Okay, so you just can anybody solve this equation and tell me what is the answer? What is omega GC?
1.6 minus 5.6.
1.6 minus 5.6.
Yes.
Okay, yeah, I'm just taking your words. Let's say minus negative value is not allowed, so you only consider the positive values. Let's say you told that your omega GC is 1.6. Okay, let's say. So once you got this, you have to calculate it. After you find out omega GC, you have to calculate the phase margin. Okay, so for one point of time, I'm stopping the screen because I want to go to MATLAB, and I'll show you how to calculate all these things, because uh, mainly this class is based on how we have to familiarize the MATLAB. Okay, all this compensator design. So now just please confirm that is my screen is visible, MATLAB screen.
Yes, sir. Yes, sir.
Okay, fine. Now you see whatever the transfer function is there, you have to what you do, you need to type it in your MATLAB. I have already typed in because to save the time. So what is this command I have written? I'm just quickly go through it. Okay, I'm clearing all. Okay, my windows, all my workspace. Okay, everything. Okay, so this is the first command is nothing but we have to clear everything, the previous whatever the values I am working with. I'm just trying to clear my screen. Then what you have to define? This is the Laplace domain. So what you have to define? You have to define S. S is this is a transfer function you have to write. So first of all, in any transfer function, all the terms are in terms of S. So we have to write a function. Let's say I'm writing a function, transfer function. This is a predefined form in MATLAB to write the transfer function of anything. So the second line is all about, you can say, if I write a comment, uh, you can say, I'll share this all this thing, okay. So you can say this is a you can say transfer function, okay, transfer function definition, okay. After that, what you do, you have to write your open loop transfer function. Let's say I'm giving a name as G, okay. Then how you write any equation, you can, this is just equation by numerator by denominator, you just write, okay. On the numerator I have just written 3 into e to the power minus 2s, and this is a divided symbol divided by s into s plus 2, okay. Once you do, then what you do, you can simply write this one, okay. Let's see, control, I'm doing x, you can just simply write margin of g, okay. Then what you do, if you do margin of g or simply bode of g, uh, okay, there are lots of command in bode plots, you can directly use bode of g, then it will give the bode plots. If you specify that margin of g, so it means in that bode plot, it will give you the gain margin and the phase margin. Okay. So exactly, if you want the gain margin and phase margin, then you have to specify that I want the gain margin and phase margin from the margin. Okay. So that's why I have to specify that from this margin g, this margin g is a function. Okay, this gives me the gain margin and phase margin. So I am just specifying here I require gain margin, phase margin. Also here you can write, if you want omega gc, or you can write omega pc, okay. All these things also you can write out, okay. Gain margin, phase margin, gain crossover frequency, phase crossover frequency, then all the four things the MATLAB will now show you. But I am just interested in, I'll show you now that because I'm interested in the gain margin and phase margin. So you write down I required the gain margin and phase margin. Okay, so these are the display. Okay, you know that the magnitude plot will be written in 20 log. Okay, so these are the things I just for displaying my graph I just have written. Okay, then let me run it and we'll see what the things is coming now. Now you can see I'm just zooming it. Okay, now you can see there are two plots is coming. One is the magnitude plot, another is a phase plot. Okay, so once you can see on the top of this border diagram, whatever I am giving, here you can see the gain margin is given to you minus 7.09 decibel, and at which frequency 0.632 radian per second. It means the gain margin at the phase crossover frequency, it means 0.632 is the phase crossover frequency, and the phase margin, okay, the phase margin is minus 86.6 degree at 1.27 radian per second. So what the value you told, that 1.6 or something, that is wrong, okay. You just recalculate your value and you can find out that this omega gc, the gain crossover frequency, it should be 1.27, it should not be 1.6. Okay, so you can check it the calculation properly. Okay, you can find out that the omega gc is 1.27 radian per second, and corresponding to omega gc you get a phase margin. Phase margin is nothing but, what is the definition of phase margin, that is coming back to my slide. uh, Phase margin is nothing but what is the phase that system is giving for the system stability, that's the definition normally. So phase margin is nothing but you have to add 180 degree plus whatever your system, okay, g of s, you have to find out the angle of that at omega equal to omega gc. So gc is the gain crossover frequency, so you have to find out at omega gc, okay. First find out the angle of the system and add it to 180 degree, that will give the phase margin. And if you put here, this is not 1.6, it is some 1.266, okay. I'm just,
Sir, 1.6 is x1, x2, sir. X1 is 1.6, x2 is minus 5.6.
okay,
And
sorry, then you find out omega.
omega is
This,
1.27.
all right, thank you. So this is the thing that is matching to your, okay. This is 1.266, okay. So now after finding out this omega gc, you can verify everything, because uh, MATLAB is a powerful tool, you can verify everything, but in your examination, that is a demerit that it is not available. So, but you have to be handful experience at how you're doing all these things. So now you can see at omega GC is 1.26 and phase margin corresponding that we got is something negative. Negative means what? Gain margin and phase margin negative means the system is unstable. So whatever the system we are seeing, this is open loop transfer function, but we are finding out this closed loop system stability by using Bode plot, and from that we conclude that the gain margin and the phase margin of the system is for a unity feedback system it is negative. It means the system is unstable. But if I coming back, to let's calculate. Okay, let's calculate what is the value of the gain margin. Sorry, phase margin. Then we'll verify there. So let me go to the next screen. What is the angle? Okay, you have to find out. Okay, 3 into e to the power minus 2 j omega. This is the value of the transfer function, and j omega into j omega plus 2. This is your g of j omega. You have to find out the angle of the system. Angle means I'm just giving this sign. Okay, angle. So how to find out? So for the denominator part, the angle will be something like that: cos 2 omega minus j sine 2 omega. Okay, I'm just expanding the term of I'll find out the angle later. Just simplifying this one, j omega and j omega plus 2. Now you have to find out the angle of each term. Okay, so let me find out the angle of each term. So this will be something, the numerator part will be positive. So you can say tan inverse, okay, minus sine 2 omega divided by cos 2 omega. This is the numerator part, and in the denominator part, what is the angle? J omega angle is 90 degree, and this angle will be tan inverse omega by 2. So now everything you take to the numerator part, so it will be how much? Tan inverse minus sine 2 omega divided by cos 2 omega minus 90 minus tan inverse omega by 2. Okay, so now after you find out this value, okay, you just what you need to find out, you need to find out the phase margin of the system. So in this phase you just put omega, in place of omega you just put omega gc, whatever the value you will get, 1.266, and find out that angle phi, whatever the angle you will get for the phase margin. What you do? 180 plus phi. This is the phase margin. Okay, I'm not calculating because the calculation will be a little bit lengthier, because you have to, anyway you have to use the calculator for solving this. Okay, so what you do in the calculator, the simplest way what you do, how to calculate this, go to the math mode. Okay, go to the math mode. Okay, in the math mode what you do, you have to write this equation. Okay, how to write this equation? You write this equation as tan inverse minus sine 2 omega divided by cos 2 omega minus 90 minus tan inverse omega by 2. In place of omega you have to put that value, and then after writing this equation you just type shift plus solve. Okay, if you do shift plus solve, it will give you the result directly. Okay, for any equation, any fourth order equation, fifth order equation, any equation of any order, okay, any trigonometric equation, in the if you have a scientific calculator, then use this powerful tool. Okay, you will get the result directly. Okay, and also if you find out omega pc, omega pc is called phase crossover frequency. Phase crossover is the frequency at which the phase angle is minus 180 degree. Okay, phase crossover frequency is defined as at where the phase of the transfer function, you can write like that, I'm sorry, the phase of the transfer function means g of j omega angle, okay, at omega equal to omega pc, that should be equal to minus 180 degree. It means whatever the phi you are getting here, if we equate that phi to minus 180, means from that you will find out that omega value, unknown value, and that omega is your omega pc. Okay, so that way you can also find out the omega pc. So once you find out omega pc and omega gc, then you can find out the gain margin and phase margin. If I coming back to my MATLAB screen, then let me show you in that MATLAB plot. Okay, you can clearly see that the gain margin is minus 7.09 decibel at omega pc. Omega pc is the phase crossover frequency. If you equate your angle of the transfer function to minus 180 and corresponding omega, you will get at 0.632 radian per second. Okay, you can solve it by using calculator and you can check it. Okay, so now this is one way that you can see that how you can vary the gain margin and phase margin from the Bode plot analysis. So what to do if you want to further analysis this tool, then what you go to tools option. Okay, take a data tip. Okay, at any point you click here in the on the denominator, or sorry, on the top graph, on the bottom graph, you can see one pointer is coming into picture, and that pointer you can drag it. Okay, you can drag it and you can see that at this 0.632, wherever this 0.632 will come, somewhere 0.632 is very low value. Okay, 0.362. Okay, 0.362, little bit. Okay, somewhere here. I don't have a mouse right now. Okay, you can drag it and you can see that what is the magnitude is coming at this point. Okay, so you can see, if we, let's say at 0.358 you will get a magnitude of 12.3 decibel, but what is gain margin? Gain margin is nothing but negative of that value. Okay, it means at 0.632, right? Not 0.632. Okay, let me see here, 0.635, the value is very close to 7.04. So 7.04 is the magnitude that you get, but gain margin is negative of that. Okay, that's why the gain margin is negative, minus 7 is coming. Okay, and similarly also in the bottom side you can do the same thing. Okay, and right click, again I can just say mouse position, can go to the tools again, data types, you can click any point. Okay, once you click any point, then what you do, you just go to the selection style as mouse position, then you can drag it. Okay, and you can find out at 1.27 is where 1.27. Okay, here is something 1.267. Okay, at exactly 1.27 radian you can see what is the phase angle is contributing. The phase angle is contributing at 1.27 is minus 268 degree. Means whatever your system is having, that system is having a phase at this particular frequency 1.27 is minus 268. Now what is the phase margin? You have to add 182 here. So minus 268 plus 180, it will be around 87.6 degree. So your phase margin is also still negative. So your system is quite unstable system. Okay, let me come back to my screen. Okay, to show you another example. Mm, okay, let me go to full screen. So here another question also I have given to you, that also same thing you have to do in MATLAB. Okay, G is equal to 10 divided by S plus 1 and S plus 20. Can anybody tell me what is the gain margin and phase margin of the system? 10 divided by S plus 1 and S plus 20. Okay, you know the procedure how to find out the gain margin and phase margin. Okay, but anyway you have to solve using the pen and paper, but better to use MATLAB to handful experience. Okay, let me go back. Let me go back to my MATLAB. 10 divided by S plus 1 into S plus 20 you have to write. So you write expression. Okay, G equal to 10 divided by, okay, S plus 1, can write S plus 1 into S plus 20. S plus 20. If I do any typing mistake, yeah. Okay, this is small as I've defined already in the second line. Okay, so comment out on the first one. Okay, because I just want a second expression 10 divided by s plus 1 into s plus 20. Run it. Okay, you can see what is the gain margin you're getting directly. The gain margin is infinity and the phase margin is infinity. What is the meaning of that? Gain margin is infinity means the gain crossover frequency does not exist. Phase margin is infinity means the phase crossover frequency does not exist. It means your system is providing a infinite gain and infinite phase margin. Means basically you cannot say the stability of the system. Okay, cannot conclude anything. So for this type of system, you require to maintain the stability. To talk about the stability, you need to add a compensator. So why the requirement of compensator? Compensator need the system stability. You have to find out anything like settling time. What is the settling time for? I just let's say imagine that your settling time is let's say 5 seconds initially. Without a compensator system, you want to reduce the settling time, let's say 2 seconds. So by adding a compensator, then which compensator you have to use? Whether you have to use a lag compensator, whether you have to use a lead compensator. So that are the things you need to do the analysis now. So let us coming back to my original slide. Let's, let's do another questions. So you'll get a feel of that. Okay. Let's. This is a very good question I collected. Okay, from a previous year question. Okay, from the NPTEL examination. Okay. So look at the question and read it, and we'll solve it. Okay. A group of control engineering students is attempting to control a plant of GS is given to you 10 divided by S into S plus 10. Okay. Now, but they are saying that you have to maintain a phase margin of 50 degree. This is acceptable. Okay. Now, the system has a controller GCS, but the group is unable to select GCS appropriately. Okay. But remember that they want to maintain a 50-degree phase margin. Okay, that is acceptable. So now he's saying that what is the phase margin of the plant. So for the compensated system, but first what you do, you have to find out the phase margin of the uncompensated system. So for the uncompensated system, let me write down that uncompensated system 10 divided by S into S plus 10. So what you do, you first find out the omega. You have to find out omega GC, gain crossover frequency, because we require the phase margin of the system. So omega GC is what? You have to write down 10 divided by omega into omega square plus 1. Make it the magnitude equal to 1. Okay, if you do the magnitude equal to 1, you can easily find out what is omega GC. Okay, so put in the calculator and solve this equation directly. 10 divided by omega into omega square plus 1 equal to 1. So what is the value? Let me you can check by in the calculator. I'll just put this in MATLAB and say what is the value of the omega GC. Let's see. 10 divided by S into S plus 10. So let me go to the MATLAB. Okay. So I have just written it 10 divided by S into S plus 10. Okay. So you can see the same thing I am doing here. I am just interested in the phase margin. So other thing I don't want. So I just putting a nullify symbol. I don't want to see other values. Okay. So I record only the phase margin from this margin. Okay, plot. So I run this. Okay. If you run this, then what you see that it directly gives you that the phase margin equal to 84.3. So what is the phase margin? Just note it down. The phase margin is 84.3 degree at 0.995 radian per second. Okay, just I have noted it down because you have to solve that question. So once you find out, this is for the uncompensated system I'm saying. For the uncompensated system, the phase margin I can see 84.3 degree. But if you want to check it that at this corresponding radian per second, what is the your plant your whatever the transfer function is given, the uncompensated transfer function, how much phase it is contributing. So what you do, you go to the again the tools, okay, go to data tips, okay. I'm just interested in the phase plot. In the phase plot, you click at any point, okay. Then what you do, you right click, go to selection style to mouse position so that you can drag it easily because I don't have a mouse. So that's why. So what you need to do, you just go to that frequency 0.995 radian per second. So now click here where is that frequency is coming 0. 0.995, you can see 0.995, okay, somewhere here 9394. Okay, let me quickly, just I'm not able to manage it because 0.995. Okay, you can do by yourself. Okay, okay, let me uh, let me see how much it is contributing at 0.997. Okay, it's a minus 95.7. You add 180 degree, then you get the phase margin, right? So in this, whatever the angle that is contributing your system, that angle is not sufficient to maintain your system stability. That's why you have to record a phase margin, let's say 84.3 degree. So you have to make addition of that phase angle. Let's say I'm adding 180 degree to that. So that is giving 84.3. But this is for the uncompensated system. Now, in the question, what it tells you, the question is telling you that you have to you have to maintain the phase margin to 50 degree. Not, I don't want a phase margin of how much, whatever the value you get, 87.6 degree. I want to design my system, I have to add a compensator that will make a phase margin of 50 degree. But if if I need to reduce the phase margin from 87.6 degree to 50 degree, you can write down here, I have to reduce the phase margin from 87.6 degree to 50 degree. How can you do that? You have to add a compensator. Okay, but what is the compensator gain? He's asking about that. Okay, the first question is done because you already find out the phase margin of the uncompensated system. Let's go to the second question. Then they are telling that you add a compensator whose gain is k. Okay, you add a compensator whose gain is k. Okay, now what is the plan transfer function? If I GCS is only k, then the total plan transfer function GCS into G of S. Okay, let me do a full screen. GCS into G of S is nothing but your K is your GCS into 10 divided by S into S plus 10. Okay, so now this is the total transfer function. For the total transfer function, what you need to do, you have to make a phase margin of 50 degree. So to reduce the phase margin from 87.6 degree to 50 degree, okay, so who will do that? This gain k will do that. So then he's asking us to find out the value of k. What is the value of k to maintain that phase margin equal to 50 degree? So what you do, how to do that? So you have to find out now the omega gc for this system. Omega gc for this system. What is the omega gc? That will contribute a phase margin of 50 degree. Okay, so for that, first of all, you know the phase margin 50 degree. If you solve, suppose this question you have to solve in the examination, you don't have a MATLAB, then how to do? First of all, your phase margin is 50 degree. So what you do, you first write down here, I'm just writing here, 180 plus angle contributed by GCS into G of S, okay, that equal to your phase margin, and that phase margin is 50 degree. It means the angle contributed by GCS into G of S, it should be equal to 50 minus 180 is minus 130 degree. Okay, I required a phase of minus 130 degree. Okay, so what you do for this question, you equate the angle of this transfer function GCS into G of S equal to minus 130 degree. From that, okay, you find out omega value. Okay, from that omega, after finding out that omega is nothing but your omega GC. This omega, whatever you get, omega GC. Then you take the magnitude of the transfer function and equate it to 1. Then that value will give you the k value. Okay, you understand the procedure, what I told you. First of all, you know that you total angle contribution by the compensator plus plant is now minus 130 degree. Okay, so from there you can find out omega GC. From omega GC definition, you make the magnitude of the transfer function equal to unity because you know omega GC in terms of k, equate it to 1, then you'll get the value of k. Let me solve this question using MATLAB. Okay, so I just required uh, a GCS into GS angle contribution is minus 130 degree. Okay, go to MATLAB. Okay, so what is the angle contribution? Now the angle contribution is minus 130. Total angle contribution, and go to minus 130 point. Okay, so here you can go to, this is the minus 130 degree angle. Okay, so now you can see here the phase degree, this phase angle is minus 130 degree. Once the phase angle is minus 130 degree, corresponding frequency. Okay, so now corresponding, I can see the frequency. The frequency here is 8.39 degree. But you go to this 8.39 degree here, okay, on the gain margin, because you have to equate it to 1. So can go to 8.39 somewhere here, 8.39. Okay, here is 8.35, 8.35. Okay, let me go to 8.39 slightly. Okay, sorry. Okay, this is 8.39. Okay, now you can see at 8.39 the magnitude is contributed by how much? 20 decibel, 20.8 decibel. Okay, so 20.8 decibel is the magnitude. This is negative, but this magnitude, whatever the gain you are adding, to make this magnitude is equal to unity. Unity means what? 0 decibel, 1. You have to make at omega equal to GC, you have to make your magnitude equal to 1 at 8.39. Okay, so what do we need to do? You have a now minus 20.8. You have to make it equal to 1. 1 means 0 decibel. Okay, so here all everything is in decibel. So minus 20.8, you have to add the minus 20.8. If you add plus 20.8, then you have to get a 0 decibel. 0 decibel means your magnitude equal to 1. So what is the angle now contribution? Means what is the value you have to add? The k value you can directly add 20.8. So if you go to here, if you add k equal to 20.8, this is in decibel. Okay, it means 20 log k equal to 20.8. Then what is the value of k? 10 to the power. Okay, you can find out what is this log k, 10 to the power 20.8 divided by 20. So like that way you can find out the value of k. Okay, you understand this question, everyone? How I calculated the value of k from MATLAB. Okay, anyway you can do calculations. I told you the procedure how to do calculation, but also in MATLAB also you can find out like that. Okay, so this is the basic principle of designing a compensator. What is a requirement? That requirement you have to fulfill by your compensator. That's it. Okay. So generally these are the things with the control system engineer they are doing. Okay, so what they're doing, they're designing a plant. Okay, that plant is relatively unstable, or they require something to reduce the phase margin to something, or they want the settling time is this much, they want a rise time of this much. Okay, they want a percentage peak overshoot of this much, so they are need to add a compensator. That compensator, you have to vary the gain of that compensator, you have to vary the location, the poles and zeros of the compensator to achieve your goal. Okay, everyone is understood?
Sir, omega GC is equal to 1, sir.
Sorry.
Omega GC is equal to 1. Why did he equate, sir?
Omega gc equal to uh, omega gc is not equal to 1. I told you at omega gc your gain should be equal to 1, not omega gc equal to 1. What is the definition of omega gc? Omega gc is the frequency at which your gain of its system is equal to 1, right? So that the thing I just uh, because at omega point omega gc I got some 8 point something. At 8 point something I saw that in the MATLAB that there is a lagging in gain. Gain is not reaching to 1. Okay, it is showing some minus 20.8. It means if I my compensator will add that 20.8, then I'll reach that gain equal to 1. So that who is doing that part? That part is doing by your k, means that compensator gain k. You understand sir right now?
Yes, sir. Sorry, for studies, so for time also the same thing for steady state error time, settling time, sir. The same procedure.
Sorry.
For settling time also same procedure. For settling
Yeah,
time too.
means suppose you're settling time. I think I have some question related to that. Means suppose let's say you want to let me do that question number 3 for you. Okay, so what is the settling time in second in a step response of the system for the value of k obtained in question number 2? So in the question number 2 I got a k value. Can anyone tell me what is this value k? 10 to the power 20.8 by 20. Can you anybody find out this value? 20 log k is equal to 20.8. What is the value of k is equal to 10 to the power 20? Let's say I'm assuming that the my k is equal to I got some 10. Okay, let me assume that. Okay, let me go to the next slide. Just put this slide here. Okay, whatever the question is now, 10 divided by s into s plus 10. So here the plant is given to you 10 divided by s into s plus 10, and you have a compensator whose gain is k. I'm assuming that the k that I got approximately, let's say 10. I don't know what is that value calculated. Sorry, your voice is not coming. Okay. Mm,
10.96.
10 point.
10.96.
Okay, 10.96. Okay, you got this value. Okay, now what is the total plant transfer function? G of s into GCS. Okay, so it will be 10 into 10.96. You multiply this two value divided by s into s plus 10. Okay, now you find out the closed loop transfer function. The closed loop transfer function for a unity feedback system, let's say 10.96 into 6 is 109.6 divided by, this will be s square plus 10s plus 109.6. Okay, so now you can see that your omega n square is something 109.6, and your 2 zeta omega n is equal to your 10. Okay, it means zeta omega n is equal to your 5. Okay, and in that question it is giving that 2% settling time. 2% settling time means your it will be 2% means it will be 4 times of time constant. Okay, I'm just giving it here on the right hand side. I'm doing 4 times time constant. So 4 times of time constant is nothing but 1 by zeta omega n. Just 1 second. So now you calculate that and zeta omega and value put 5. So this will be how much? 4 divided by 5. Okay. So 4 divided by 5 is how much? 0.8. Okay, 0.8 second. So you got the settling time is 0.8 second. Okay. But what is the question is saying that? The question is saying that, okay, so corresponding to initially, okay, corresponding to initially, what is the settling time? If I have a system, only 10 divided by s into s plus 10. I don't want to add the compensator, okay. Let me do in a different pen for understanding. Suppose I have only g of s. If I have only g of s, what is written here? You find out the closed loop transfer function of that gs. So it will be 10 divided by s square plus how much? 10s plus 10. So by adding that compensator, is that value of settling time is changing? Is the settling time is changing? No, not at all changing because 2 zeta omega is again 10. So again you got 0.8 second. It means by adding a compensator, only the magnitude, a constant, it will not affect your settling time. It might be something that you need to add a pole or you need to add a zero in the compensator to affect your settling time. So that thing is varied from different question to question, but for this question you can verify that your settling time is remains same. Settling time does not depend on the magnitude of the compensator gain. So, but to change the settling time, you need to add a pole or zero into your compensator. Okay, let me quickly go to the next question. Okay, okay. This question, I think. Okay, let's do it. Do this question. So read the question. This is open loop transfer function 1 divided by s into s plus 1, right? So it is desired that, read the question, that the compensated system has a velocity error constant kv equal to 10. This is not given, any gain is not given to you. He has directly given that for the compensated system has a velocity error constant kv equal to 10 and a phase margin of 40 degree. You have to maintain the phase margin of 40 degree. Okay, that is important. Then the gain crossover frequency of the uncompensated system is what? This is the first question. Okay, question number one, question number two, and question number three. You can now you can do this. Tell me what the answer. How to approach this question? Can anybody tell me? You first find out omega gc because whenever a phase margin is coming into picture, you just find out the omega gc, the gain crossover frequency. Okay, then only you can able to comment on the phase margin, right? So first of all, find out 1 divided by omega into omega square plus 1. Okay, if you put this omega nothing but equal to omega gc and make it equal to 1, then you find out omega gc. Okay, so this will be omega gc square into omega gc square plus 1 equal to 1. Simply same thing actually you got here. What is omega gc? Can anybody solve and tell me? Otherwise I'll put this in MATLAB and tell you what is omega gc. What is the value of omega gc? At least please someone reply what is omega gc.
fourth order equation it will come, and then we have to apply.
No, no, sir. Actually, I told you that you don't waste your time like that. If you have a scientific calculator, then directly put this equation. And this is a fourth order equation. Omega gc fourth plus omega gc square minus 1 equal to 0. Write this equation in your calculator. Then type c
minus 1 by
plus.
2.
No, always the negative term you have to discard. Only positive terms you have to tell. Okay, you can try. You can see that because
0.61.
point
0.61.
0.61. Okay, let me check. I don't know. I don't know the answer. Let me check in the MATLAB. Okay, but you might be you're doing something wrong. Let's see. Let me 1 divided by s into s plus 1. Go to your MATLAB. Okay. So what I do, I need to just type that transfer function. Okay. You just type. You first define your. You just define the transfer function in Laplace domain. This is the command. And here this g whatever I written here, this is 1 divided by s into s plus 10. Okay, I required only the phase margin, that's why it required a phase margin. Run the command. Okay, then you can see, if I zoom it, you can clearly see that the phase margin is coming 51.8 degree at 0.786. Okay, 51.8 degree at 0.786. Let me write down 0.786, and the phase margin I got for the uncompensated system is how much? 51.8 degree. Okay, this is for the uncompensated system. Okay, now he what the question is telling, that you have to add a compensator. Okay, for the compensated system has a velocity error constant kv equal to 10. Okay, and a phase margin of 40 degree. First, what you do, you just uh, make that velocity error constant equal to 10. First do that. Go to the next slide. Just 1 second. Let me go to the full screen mode. Okay. So what you do, you just write down that gs is how much? 1 divided by s into s plus 1. You need to add a compensator gcs. Okay, multiply that. Okay, gcs into g of s. Let's say its gain is k. I don't know what is the gain. Okay, you write down that k into s plus 10. Now this is a compensated system. This total is your compensated system. For this compensated system, it's giving the velocity error constant equal to 10. Velocity error constant means what? What is the definition of velocity error constant? Limit s tends to 0, s into total gcs into g of s. That is equal to 10 is given to you. So if I do that, then at this this value k, if you put this at this value, okay, limit, apply limit. So it will give you k divided by 0 plus 1, because a is equal to 0, you have to put that is equal to kv. Okay, kv equal to 10. So this implies your k equal to 10. Okay, now you got the value of the k equal to 10. So now what is the compensated transfer function? gcs into g of s is nothing but 10 divided by s into s plus 1. This is the total plan transfer function. It's a compensated system, you can say. Now for this you have to make the phase margin equal to 40 degree. Okay, in the question he is telling how to do that. You have to maintain a phase margin of 40 degree. Okay, so how to do that? How to do the phase margin equal to 40 degree? You have to go in the reverse back. Okay, so what you do? What to do? You go back to the question and see what is the phase margin of the uncompensated system you got the value. Okay, what is the value of the compensator gain needed to achieve the required on the steady state? You got the compensator gain as 10. Okay, so for this you got the compensator gain as 10. And what is the phase margin of the uncompensated system? You got some value. Okay, what is the value from the MATLAB you got? It's got 51.8, right? Okay, so all these three question is over. Okay, any fourth question? Yeah, this question is important. What is that question? That transfer function what you got. Okay, what is the transfer function you got? You got some transfer function is something like that, 10 divided by s into s plus 1. Okay, this is the total transfer function. Now here in this transfer function you have to add this, in the compensator you have to add this value. Okay, so what is this beta and t? Okay, what is this beta and t? You need to understand. You need to design a compensator now whose gain is already 10. Okay, you know that the gain is 10, you already got from the last slide, but you have to add something here. What is that value? You know that in a standard compensator, what is the formula? 1 plus ts divided by 1 plus beta into ts. Okay, so now you have to check whether you are adding a lag compensator or lead compensator depends upon the value of beta. If now here beta is now here in this question, beta is greater than 1 because beta value is given the question is 10, 7. The 7 is greater than 1. Once beta is greater than 1, it means it is a lag compensator. So that these are the things which already you have discussed in 2 weeks before. Okay. So when I was taught about lag and lead compensator. So okay. So once you check that beta is greater than 1 is a lag compensator. Now you have to design that. So it means now the transfer function is how much? 1 plus ts divided by 1 plus beta ts, right? What is the value of t is given to you? T is given to you 10 and beta t is how much? 70. 1 plus beta into t, 70 into s. Okay, this is the compensated transfer function GCS. Previously you have 10 divided by s into s plus 10. Now you have to add 1 plus 10s divided by 1 plus 70s. This is now your total system. Okay, so for this system you need to find out the phase margin. Okay, because why you need to find out the phase margin? Because you can clearly see that in the question he is giving you that what is the phase margin of the lag compensatory system given the gain crossover frequency of the overall system is 1. Okay, we have to find out the gain crossover frequency of the total system. Gain crossover frequency of the total system is given to you 1. Omega gc is given to you 1. So how to find out the omega gc? You have to take the magnitude of the system. Okay, so you have to find out the magnitude of the system and it's equal to 1. So you know that phase margin is nothing but 180 degree plus whatever the angle of the total system at omega gc, at omega gc. Okay, and omega gc is given to how much? 1 is given to you. What is the phase margin is now? Can anybody tell me what is the phase margin? 180. What is the angle of the total system? I'm writing directly writing. Okay, because this is my total system. I am writing the angle of the total system. I am taking everything into the numerator. So minus 180. For this s will contribute 90 degree. Whenever it is going to the numerator, it will be minus 90. For this s plus 1, it will be contribute to tan inverse. Okay, imaginary part by real part. This will be omega. If you go to the numerator, it will be minus tan inverse omega. Okay. But what is the omega? Omega is nothing but your omega GC, right? Similarly, you find out for 1 plus 10s and 1 plus 70s. 1 plus 10s, 10s, 1 plus 10s in the numerators. Okay, so it will be tan inverse 10 omega GC. Okay, and this 1 plus 70s is in the denominator. If you take it to the numerator, it will be negative. Okay, so minus tan inverse 70 omega GC. But what is the omega GC is given to you in the question? Omega GC equal to 1. Put the value of omega GC 1 everywhere. Find out the phase margin of the system. Okay, it will be 180 minus 90. As tan inverse 1 is 45. Okay, tan inverse this will be 10 minus tan inverse 70. Find out this value and it will give you the phase margin of the system. Okay. Okay, you can find out by yourself what phase margin. Let me quickly tell you something, okay, which is very important from this question point of view. Let me go to the next slide. So this is a question, but before coming to this question, let me tell about little about that lag compensator, what I told you previous slide. Lag compensator, I told you the transfer function 1 plus ts divided by 1 plus beta ts, where beta is greater than 1, then it is a lag compensator. Okay, if you do the pole zero analysis of this, let me quickly do the pole zero analysis of the lag compensator. So this will be this lag compensator to always give a phase lag. Okay, whatever system, let's say your system is having originally zero phase, then this lag compensator will add some negative phase. Okay, let's say it will add some minus 30-degree phase. Okay, so it means you have of course if the pole is very close to the origin, then you have a zero. Okay, this is the lag compensator transfer function. Okay, if you can check by yourself. Okay, you take any value t, previously it is 1 plus 10s divided by 1 plus 70s. Okay, so you can find out which one is closer and which one is okay. So 1 by 70, 1 by 70 is one pole. Okay, another pole is 1 by 10. So which one is closure? 1 by 70 is closure. That's why this pole you can say 1 by 70, this will be 1 by 10. Okay, like that. So always in a lag compensator, the pole will be very close to the origin. Okay, in the negative axis, because all the poles and zeros will be lie on the negative half, because these compensators are stable systems. Okay, right. So now once you find out this pole zero location, you quickly draw the Bode plot of this. If you quickly draw the Bode plot of the right hand side, then what you got, you can see your initially you can assume that system having a gain of 0, then you are encountering a pole. It poles means minus 20 decibel per decade it will go. Okay, then you are encountering a 0 of same slope, you can go plus 20 decibel per decade, like that. So this is your system. What, this is your system Bode plot. Okay, so from this Bode plot, what you need to find out, you have to find out the frequency in radian at which the maximum phase lag occur. If I draw the phase plot of this transfer function, then what will have here up to here to here, there will be no change, nothing will be there. From here to here, one pole will be there. So now the pole something will coming like this. So this is the phase plot. So if you do the phase plot, you can see that at this point, here there is a maximum phase lag occur. Okay, and this is the phase lag that the compensator is adding to you. This is the maximum phase lag it can add. Okay, this is the maximum phase lag it occur at one frequency, that is called omega m. Okay, why do you find it the omega m? This omega m is nothing but, so from, what is the pole location? 1 plus ts, 1 plus beta ts. If you do the pole location of here, this will be minus 1 by t, and this will be in the denominator, this will be minus 1 by beta t. So there are two poles. Let me alpha 1 and alpha 2. These are the, so 1 plus ts, this is the 0, and 1 plus beta t is the pole. Okay, so here these are the location alpha 1 and alpha 2. Okay, so what you do, you just take the geometric mean of that two, 1 by t and 1 by beta t. If you take the geometric mean, then you will get 1 by t root beta. Okay, so this is the omega m value. So he's saying that what is the frequency at which the maximum phase lag occurs in the compensator. This is the formula you have to use. Omega m equal to 1 by t and beta. You know the what is the value of t. You know what is the value of beta. Beta is 7, t is 10. So put that value 1 by 10 into root 7. So this will get the omega m value. This omega m is the frequency at which the maximum phase lag will occur. The same thing for the lead compensator. This omega equal to nothing but 1 by 2 delta b. It always same for both lead compensator and lag compensator. These two values are same. But in lag compensator, beta is greater than 1. That's why this pole is coming nearer to the origin. But if a lead compensator is there, then 0 is closer to the origin and pole is far away from the origin. Okay, that's why beta is less than 1 in that case. Okay, you just remember these two concepts. Okay, how to find out the frequency at which the maximum phase lag occur or maximum phase lead occur. Okay, let us be coming to the next question. Is there? Yeah. So this is a very simple question. I already solved it. Okay, so what is the value of k that will result in a velocity of a constant of 10? Okay, you can do by yourself. It's a very simple question. For this case, you find out limit s tends to 0, s into g of s, that is your kv, and kv value is given as 10. Find out the k value from that. Okay, this is a very simple question. K is by default it will be 10. The same value will come. Okay, is it clear how do I solve the question number 6?
Yes.
Yeah, right. So see, nothing is much there in this part. This only the part is that this thing actually, this part compensator design, you can three things they can ask you. You have to find out the compensator gain, the compensator, whether you are using a lead compensator, lag compensator, what the frequency of lag, like that. And other thing is that the main purpose of this, that you have to familiarize with the MATLAB. How in MATLAB you are doing body plot, how you are sweeping, how much gain is required, how much phase is required, how much phase margin is required, how much gain you have to adjust to make the system stable, or to, but to arrive at a particular means specific requirement of the system, you have to use the MATLAB very friendly. Means frequently you have to use the MATLAB to acquainted with the gain compensator system. There is another tool in MATLAB that is called CISO tool. Okay, just I'm writing the names, you can explore yourself. Okay, SISO, CISO tool. Here what you need to do, you need to do the design of the compensator, like not compensator, you can say controller. Like say you can use a PI controller. Okay, you can find out, you can tune the KP and KI values. Okay, okay, KP and KI value. You can use a PID controller. Okay, you can tune your KP, you can tune your KI and your KD values. Okay, so that is also a powerful tool. Okay, in place of bode G, what you do, or in place of margin G, what you do, you have to write CISO. Okay, tool G. Okay, then a controller window will open. In that, a PI controller you can add, or you can tune the KPK values. You can do PID controller based on your applications. Okay, so these are the little bit design aspect. Okay, but for your examination, I don't think the question will come by using MATLAB. You have to solve everything by your hand or by using calculator. Okay, so let me uh, go quickly.
Sir,
Yeah,
my one question, suppose the graph is given in question directly, magnetic plot and phase plot is given in the question.
right.
And suppose I want to use MATLAB, because what happens by only by observing diagram.
Right, sir.
And many times scales are also not mentioned in the assignment.
Right,
That
sir.
means starting point या फिर जो भी decade का जो points है अपने decade frequency जो रहते हैं,
Right,
so
sir.
that points are not mentioned, so it is very difficult to approximate the values, and
Okay.
that's why we may not able to get the correct answer. So is there any tool to find out, or can we get that body plot directly by using MATLAB?
Uh, Not by using MATLAB can, because uh, if they have not given exactly the location, exact point, then nobody can able to find out. Okay. So
So
uh,
in that case, it will be very difficult to get the answers also.
so let's me, I don't exactly understand your point. Let's see. Let's say suppose your diagram is given to you like that. Okay. This
Yeah,
value
suppose
is
diagram is given, magnitude plots and place plot are shown in the diagram,
right.
and then some questions are asked, but the values which are shown in the graph are not that visible, or we are getting some confusion for the exact approximation. Likewise, suppose you are drawing the graph like this,
Right.
and omega is shown. So what is value of omega? It is not possible to find out. Such kind of confusion that I am personally facing.
Okay, in that case, you have to write in the forum. Okay, you can write in the forum. You
Okay.
can discuss with your friends, other people are there, whether they can able to understand. Okay, otherwise you can directly write to NPTEL that this graph is not visible. Provide a clear views. Okay. Otherwise,
Okay,
what
fine,
I
fine.
do generally, suppose there's every question you can solve it. Okay, you can take some approximation. Let's say this point is 10 and this omega is not given. Always in a powerful Bode plot is that always you use the concept slope. Slope is nothing but d omega. What is the slope? Dm by d log omega, right? Magnitude divided
Ah,
by with respect to omega. Okay. So what you do,
okay,
you always take this concept, you find out this position magnitude, this position frequency, and this position frequency. You always compute the slope. From this slope, did you see that slope is changing or not? If the slope is
okay,
changing, accordingly you can compute the other values. Let's say this slope is minus 20, again from that it changing to let's say something minus 40, minus 20 to minus 40. Then in that case, some other point is there, you can.
even sir, what happens where you are writing minus 20 slope now? Even that minus 20 slope, whether it is sure it is minus 20 or something different that slope, that also we are not able to find out because the values are not shown. Na? That's why it may be the problem from uh, what we should interpret from the graph. That may be the problem because of that.
Okay, actually, I have not checked the assignment questions. Okay, I'll
Okay, sir.
check it today. Okay, I'll check it tonight. And one thing you do,
Okay.
if you don't understand, you just ask in the forum. Okay, I don't.
Forum. Okay, okay.
Okay, you can ask other people's. Okay, other people are there. They might be understand. Okay, otherwise you can directly write to the NPTEL team support that this graph is not clearly understandable. Maybe they will help you. Okay, I cannot
Okay,
help
fine,
you
fine,
because
sir.
yeah.
Okay, sir. Yes, yes.
Okay, so for
Okay, sir.
today this is all about the discussion. There is nothing to add more, nothing to add less. You can do by yourself. Okay, this is just a compensator design like root locus design. This also by using bodyplot design. Okay, so do your question by yourself. Okay, solve the assignment all best. Okay, I'm just stopping here. I have nothing to say much more about this.
So
Okay,
can you show that SISO tools in MATLAB?
CISO tool. Okay, just 1 second. Okay, it is here like that. Suppose you have a compensator. Let you have to add a compensator. Okay, so let me go to the first question. In place of this comment, let me comment out this one. You can add CISO tool. Okay, and write out the transfer function. Okay, then what you do, you need to run the system. Okay, when you run the system, uh, it depends on your memory. Okay, because I am using a license for some IIT Bombay, that's why for me the MATLAB is faster, but it will always take a long time to open. Okay, because the four windows will open. Okay, you can see. So previously this page is called control system designer. Okay, Also, in place of CISO tool, also you write control system designer, and in bracket you write G. That also same thing will open. Okay, so you can see here. So lots of things are open on one single plot. Okay, you can do the Bode plot. Okay, you can analysis with the left hand side whatever you are seeing here. These two plots are the magnitude and the phase plot. On the right hand side it can gives you the root locus, also the step response. Okay, so everything is given to you now, you can see. So in all the single plot you can analyze body plot, you can do the root locus analysis, you can see the system is stable, how much it's over damped, under damped, what is critically damped, you can check it. So if you have to add a compensator, then what you do, you go to the tuning methods. Okay, in the tuning method you go to PID tuning. Okay, because in the PID, under the PID tuning section, what you have to, you can see you have a P option, you can I option, you can a PI option or a PID options, whether you have to choose the whatever you controller you want going to use, whether you want to only proportional controller or only PI controller or PID controller, like that. Okay, so now here it depends on that what is the requirement. Suppose you want to design a PI controller, you require a bandwidth which is very less or more, or depending upon the system. Suppose you want to go a voltage control, in voltage control of any uh, it requires a less bandwidth, but if you go for a current control, a high frequency current control, you require a faster bandwidth. So in that case you need to specify the bandwidth. Okay, so in the time you can see sorry, you can go for PI. Okay, choose everything, update the compensator, it gives you the values of KP and KI. So everything it will change it accordingly on your system dynamics, it will change. You can see that when I click the PI, I set some values. Okay, then it will give some values of directly the compensator KP plus KI by S. You can see this is the gain and this is KP plus KI by S. So from here you can directly see that what is my KP and KI to make the system stable, or you have to require a phase margin of, let's say you require a phase margin of 60 degree, then you have to adjust your phase margin to 60 degree by here, by dragging this value. Okay, you can drag it and drop it. So there are lots of things you can do by yourself. This is not a, if I'll tell like that you'll never not understand anything. You have to take a particular problem. Okay, you try to design a PI controller or PID controller. Okay, this is called the dynamical modeling of the system or small signal modeling of the system. Okay, so the transient response analysis, we are just using this method to get the KPKI tuning. Otherwise what people are doing, and whenever they are designing any closed loop control, they are hit and trial method, they are do the tuning of KPKI or whatever other values. But if you have a system, you know the plant transfer function, then you can design your own compensator and KP and KI value and put that KP KI value in your somewhere. If you do a closed loop control, that are the initial value. Might not be the system will be stable at this point, but it's the initial value, initial case you can say. If you play around this KPKI, you can get the system stable. It's like that. It's very close to your accuracy. It's not something different. Okay, so you can do that. Okay, you can do by yourself. Okay, how this ISO tool or this how this control system designer will be work for design. Okay, any other doubts, or I have to stop
Sir,
Sir,
here?
the
Yeah,
link of recorded videos of last week was not uploaded in the Excel sheet. So
actually
kindly do
yeah, actually I have uploaded, you can check it. Okay, I think 2 days back actually I
it.
just
Till last assignment it was not there. So can you please upload this link on our Excel sheet at
yeah,
earliest?
this link I will upload today. Okay, don't worry. Okay,
Yes. Thank you, sir. Thank you.
okay, we'll stop the session here. Thank you everyone
sir,
for joining.
sir, the peak overshoot, how do you reduce it?
Which one?
Peak overshoot.
Oh, peak overshoot will depends upon lots of factors, right? Peak overshoot is nothing but there is a formula e to the power minus 5 zeta by 1 minus zeta square. You can vary your zeta, where zeta is depends upon our frequency, damping frequency, initial parameters, all these things. I cannot say that how to reduce it directly. You have to vary all these parameters. What are the parameters? The peak overshoot is depends. That parameters you can change. Okay, accordingly
The
you can reduce the peak overshoot.
dominating parameter will be only zeta.
Right. You can zeta. Do you have a control over zeta, and zeta how the zeta will be vary? Okay, you can see zeta is nothing but the angle of cos theta between tan and sine. Okay, any dominant pole, just everything is related to your dominant pole. You can adjust your pole locations, dominant pole location, zeta will be accordingly vary, omega will be making a circle. Okay, so these are all system parameters, they are linked to each other. Okay, you cannot say that how to reduce. Okay, one thing. Okay, any other doubt? Let me come back,
Thank you.
stop the recordings. Okay, thank you.